All right, so today we're covering trigonometric word problems today. We're going to look at real world scenarios where we're actually using these trigonometric graphs that we've been covering the last couple of days. It's a good one today. Here we go. So we're going to investigate how to apply our understanding of sine and cosine functions to real world situations. We will need to take full advantage of the characteristics of sine and cosine graphs in the form y equals af bx minus c plus d, including their periodic nature, so in other words, the fact that they repeat, their starting positions. Remember, sine starts at the midline going up, cosine starts at your maximum going down. Amplitude / vertical stretch, your A value, your period length, which is related to your B, phase shift, which of course is your C, and the midline, or in other words, the vertical shift, which is the D. We need to take full advantage of all these things today. Let's not waste time. Here we go. So periodic functions, I want you to recall that trigonometric functions are periodic. This means they have a repeating pattern over some period, right? A period being the amount of time it takes, or the length, I guess, on the x-axis that it takes for one full cycle to occur. There are a lot of things that behave in a periodic manner. For instance, water depth near the shore as the tide goes in and out. Like this picture right here, this is from the Bay of Fundy. Bay of Fundy, of course, is between New Brunswick and Nova Scotia. It is actually well renowned for having one of the highest, or if not even the highest, change in tides throughout a day. It's quite remarkable. But of course, since that tide goes in and out and up and down, so the water level goes up and down throughout the day, that is a periodic nature to it, right? Now, another one would be the height above ground of a passenger on a Ferris wheel. That's a common thing that just seems to come around where we always deal with Ferris wheel questions, but whatever. Another one, the position of a pendulum going back and forth, so something on a string or something going back and forth and back and forth. The position, of course, is periodic, whether it's the height or the horizontal position. And then another one, something you wouldn't really think of too much, the voltage produced by an alternating current, or AC, right? So AC electricity works by having a positive voltage and a negative voltage alternating numerous times per second. As a matter of fact, we have 60 hertz voltage with our alternating current, at least in North America. That means it's doing this 60 times per second. Kind of crazy. But anyway, the voltage is going back and forth, back and forth. And even just looking at a graph of the voltage, the positive voltage versus the negative voltage, you can clearly see it is a sine or a cosine wave. Well, more accurately, notice it starts at midline going up. Holy smokes, look at all these connections, right? A midline going up, that would be a sine wave. Wow. Anyway, moving on. So, huge wall of text here, but I'll run through real quick. Either sine or cosine can be used to model these. Now, sometimes I'll ask you, please use sine, please use cosine, but you have total freedom because remember, sine and cosine are the same graph. They're just phase shifted left or right by pi/2 or 90 degrees. Really important here, this one, absolutely crucial. Unless it explicitly uses degrees, we always need to be using radians for modeling these. Radians are used for modeling real-world situations, unless that real-world situation has to do with degrees for some reason, right? Radians are just more practical because remember they're based around the circle itself. Degrees were arbitrary, that's why we're using radians for this. Now, generally, you'll want to avoid phase shifting if at all possible, so we can take advantage of the key visual difference between sine and cosine in that sine starts at the midline going up, right, and cosine starts at the maximum going down. If you can avoid a C value, if you can avoid that horizontal shift left or right, by all means do, right? You want to avoid that as much as possible. But otherwise, you can still use it if you need, right? So we can transform sine and cosine to fit a specific scenario using that general form. A is your vertical stretch, your amplitude. Yesterday, I showed you that your amplitude is your max minus your min divided by 2. The good news is a little bit of intuition can go a long way here. If you can't remember that, you can always intuitively find your vertical stretch, especially if you were given a picture. B is related to the horizontal stretch being 1 over B, and to the period. Remember, period is 1 over B, your horizontal stretch, times by the original period of 2 pi, or if for whatever reason you're using degrees, it's 1 over B times 360 degrees. C is, of course, your horizontal translation, or in other words, the phase shift, and D is the vertical translation, which is the midline. We also looked yesterday at how the midline D is your max plus your min divided by 2, which makes sense because that's like saying your midline is your average between your max and your min. That's an easier way of remembering that one. All right, so let's do an example right off the bat here. The pendulum of a grandfather clock swings with a periodic motion that can be represented by a trigonometric function. At rest, the pendulum is 16 centimeters above the base. The highest point of the swing is 20 centimeters above the base, and it takes 2 seconds for the pendulum to swing back and forth to its starting point once. Assume the pendulum is released from its highest point. Write a cosine equation that models the height of the pendulum as a function of time. I'm a very visual person, so I like drawing a very simple picture right off the bat. I know I didn't provide a grid on this one, but that's because you don't have to, right? That was a horrible line, but you're going to hopefully get the idea here. We know at rest it's 16 centimeters above the base, and then at the most it's 20 centimeters above the base. Okay, so the maximum height is going to be 20, the minimum height is going to be 16. So if we keep that in mind, we'll just kind of scale this up. We're going to jump to say where this is 16 and this is 20. We're assuming that the pendulum is released from its highest point, and we're also saying that we're doing this as a function of time. So time is going to be our x component here, and our cosine height, rather, is going to be our y. Anyway, so we're releasing it from its highest point, so that means when x is 0, when your time is 0, we are going to start right there. It's going to eventually make its way to its lowest point before swinging back to its highest point. Now, just to make the most of this little graph I drew here, remember it takes 2 seconds for the pendulum to swing back and forth to its starting point once. That was a horrible underlining as well. I'm not doing too well today. Starting point once. But here's a really tricky part of these questions, and I chose this one first on purpose. This pendulum is going to be released from its maximum height, let's say over here, swing down, and then come back in 2 seconds. But notice when it swings down on the other side, it's going to hit its maximum height of 20 again. So really, this 2 seconds isn't just one period. It's actually going to be 2 periods, at least in terms of our sine wave, because what's going to happen is we're going to look at it come down to its lowest point, back to the highest point on the other side of the clock, back to the lowest point in the center, and then back to the highest point. Okay? So this right here is actually your 2 seconds. Now, visually, just by looking at this graph, you can see that this other one, so the amount of time it takes to get to this other maximum height, is going to be, of course, 1 second. And from that, because we're going from a max to another max, we can say that our period is going to be 1 second, because it takes 1 second for it to continue one cycle from a max to a max. A period is not, at least in mathematics, it's not how long it takes for it to come back to its starting point here. In physics, it would have been otherwise, but again, physics is a different example altogether for those of you in that. But period in math, of course, is just based off of the graph itself. So it's going to be coming down to its minimum height of 16 and then up to 20 on this other side here after 1 second, and then back to its starting point after 2 seconds. So just thought I'd throw a little bit of curveball at you right off the bat here. So we're trying to come up with a cosine equation that models this. So we know our period, and remember, period is 1 over b times by 2 pi. And perhaps it's easier to say that that's 1 equals 2 pi times 1 over b is 2 pi over b. So then we can times by b on both sides, and you're going to see that b is actually going to be 2 pi. 2 pi is actually what we're going to be putting into our equation, and it's not uncommon at all to actually have a pi built in to these equations here. I know how strange that might kind of seem. But anyway, so we know b is 2 pi. Now let's also figure out our other components. Remember, we need a, b, C, and D. B we've already got. The next one we'll address is C, especially because when we have our graph, I hope it's a little bit more obvious to you. Since it's set a cosine equation, cosine starts at its max, and notice because we were told the pendulum was released from its highest point, we're already starting from its max. That tells us as long as we're dealing with a cosine equation here, there isn't going to be a C at all. As for our A and for D, there's some formulas that are based around your maximum and your minimum. Clearly, our maximum is 20, and our minimum is 16. D is probably the easier of the two to find, at least in my opinion. Remember, D, your midline, is the average between those two. So you can just say it's your max plus your min divided by 2, which is 20 plus 16 is 36. 36 divided by 2 is 18. I always ask myself, this midline, does it make sense with this? Well, of course it does. 18 is right between 16 and 20. So this actually makes perfect sense as a D value. So I'll put a box around that too. And also the other formula A is just the same thing as this, just the conjugate of it. So it would be 20 minus 16 divided by 2. 20 minus 16 is 4 divided by 2. Of course, A gives us 2. But if you knew your midline and you knew your max and your min, you didn't even have to use this formula, because remember, your amplitude is just how far above or below your midline you go. And if your midline is 18, you're going 2 up to get to 20 and 2 below to get to 16. So you could have just intuitively found that as well. Long story short, if we're going to write it as a cosine equation, remember the general form of this is y equals a f, oops, went too fast, b x minus c, square bracket, plus d. where our function in this case is cosine. So in this case, you just throw in all the numbers we found. Y equals 2. F, of course, is cosine. B is 2 pi. X is just still X. You could also call it T for time. You could call this, H for height, whatever you want to call it. I'll just stick to X and Y because it's easier. C doesn't exist in this one, so I get to close the bracket off right there. You don't even need the inner bracket in this case. You could have just said 2 pi X. But whatever, it doesn't hurt to be more precise. Then plus D, so plus 18. So that right there would be your answer. Moving on, part B. Write a sine equation that models the height of the pendulum as a function of time. Now here's the funny thing with these ones. Sine and cosine model the exact same thing. All of the characteristics between your sine and your cosine function are going to remain the same. So in other words, A is still going to be 2. B is still going to be 2 pi. D is still going to be 18. All of those things, especially if I go back to the picture here, all of those things are still going to accurately represent this picture. It's just we want to represent it using a sine equation instead of a cosine equation. Well, the only thing that changes sine and cosine is your C value. So the difference on this next question is we are going to want to have some sort of a C value. Now let's be careful on this one. You can go either left or right on this. Now, what I want to make a little bit more clear is if we were to move the sine function to the right, we would want to consider our original starting point to the left rather, or would it be to the right? No, it would be to the left. Sorry, my mistake. If we wanted to move it to the left, we would want to consider our original starting point, this point here, because sine starts at the midline going up. So just before our time of 0, there would have been a midline going up, just right over here. Now, we need to figure out what that distance is. From this graph, we knew from the maximum to the next maximum is 1. That tells us that the distance to this minimum point here is 0.5. And then that also tells us that the distance from this maximum to this midpoint going down would be a 0.25, right? Logically, if this is 0.25 to here, then it's also a 0.25 to here, but it would just be a negative 0.25. This is where you've got to be kind of careful. If this is actually a sine function, we would have had to have moved that sine function to the left to move that original starting position to this one over here. So we could say that we moved it, I'll just switch to the next slide. We could say that we moved it to the left by 0.25. If you don't like that, and you're more saying, you know what, I want to consider this midline going up to be my starting point, then you could figure out how far to the right you moved it. Well, this one being right in between 0.5 and 1 would logically be 0.75. So if you prefer to say that this was your starting point, you could have just said that you took the sine wave, which remember is your midline going up and there, and you moved it to the right by 0.75. So that is another total option that you could have here. So right by 0.75. Both of these are going to spit out the exact same thing. And if you're not sure, you could always throw in some test points in your calculator and then see if the two different equations give you the same thing. But you can take my word for it, they actually will. I'm going to stick with this one because I think that's a little better because it was closer. So left by 0.25 tells me that C is actually negative 0.25. Or in other words, we can say my equation is y equals 2 sine, because remember we're using sine this time, square bracket 2 pi x, and then plus, because we're going left, so plus 0.25, and then plus 18. Again, if you don't want to use that equation, you could write it to go to the right instead. So you could say y equals 2 sine square bracket 2 pi, that's your b, x minus c, so minus 0.75. That would mean to the right by 0.75 plus 18. That's another possibility. Both of those answers are correct. The bottom line here is I want you to think of both sine and cosine as being the exact same wave, just shifted left or right, depending on your perspective. Personally, I think this question is much better suited to using cosine because it already is starting at your maximum point. Really, there's no business in making this a sine function because sine starts at a midline going up. And if we don't have to have a C value, if we don't have to have this piece here, then why use it? There'd be no point in doing so. Okay, anyway, we're going to try another example here. Next example is a windmill example. So starting at the bottom of its rotation, the tip of a blade on a windmill is 8 meters above ground. At the top of its rotation, the blade tip is 22 meters above ground. The blade rotates once every 5 seconds. Draw one complete cycle of this scenario. Well, all right, so we know our minimum point, and we also know our maximum point. So let's throw that in here. We'll say this is our min at 8 meters, and our maximum up here at 22 meters. And we were told that it starts at the bottom of its rotation. So it is actually going to be starting down here. We're going to say it rotates once every 5 seconds. Well, if you think of a windmill spinning around here, it's going to start at the bottom. So it's going to have its lowest height, then it's going to have like its middle height, and then its highest height, and then its middle height, and then its lowest height. So one full cycle is exactly one full cycle. Unlike that grandfather clock question we just did, one cycle is one cycle. So we'll say our next midpoint, or our minimum point is just down over here, which means the middle point between a min and a min would be a max. So we'll say that's there. And the wave will look something like this. It's not perfect, but you hopefully get the idea. It's a little bit off base, but whatever. You just hopefully still get the idea. Anyway, that whole cycle happens after 5 seconds, which means your maximum happens at 2.5 seconds. And I guess if we wanted to find your midline, just like that, you wanted to find your midline, the midline is going to happen between 0 and 2.5 seconds. That would be 1.25. And then if we added another 1.25 to this, that gives us, I guess, 3.75. Those would be our important points here. And notice before, I know I said it in a previous lesson, it's nice when you take your full period and you divide it into 4 chunks. Yes, it's not even because I didn't draw this very well. There was no grid here to help me. Whatever, deal with it. But breaking it into 4 different pieces is actually a really useful way of visualizing what's happening here. So that is one complete cycle of the scenario. We drew it. We don't have to go any more accurate than that. That is 22, just by the way. It doesn't look very clear, but 22. Now, given that you're starting at the bottom, determine a cosine equation for this scenario. Well, neither sine nor cosine start at the bottom. Sine starts at a midline going up, cosine starts at a maximum. But what's kind of interesting is I'm glad they said cosine here, because cosine usually starts at the maximum, but if we vertically reflect it, like if we flip it upside down, then of course it starts at a minimum. So instead, because we're starting at a minimum, we're going to do a vertical reflection on this cosine for sure. But either way, we should also find all of our other important details. Remember, D is your midline. So we want to find the midline between 22 and 8. Really, that's just the average between those two. So we can say 22 plus 8 divided by 2. That's 30 divided by 2, or in other words, 15. So just like that, we found what our midline is here. And if we wanted to find our amplitude now, we could do 22 minus 8 divided by 2, or you can just visually look and see, okay, how much up and how much below is it going to go? Well, I can tell by visually inspecting this that A is going to be 7, because it's going to go 7 up to get to 22 and 7 below to get to 8. So we know A, we know D. We don't know the B value though, but remember B value is related to the period. It didn't say whether we're in degrees or radians here, so we have to assume radians. So I'm going to say that the period equals 2 pi divided by B, or in other words, 1 over B times 2 pi. The period we know is 5 seconds, so 5 equals 2 pi over B. Times by B divided by 5, that gives us B equals 2 pi divided by 5. So we know D, we know A, we know B, and since we've already determined it'll be a vertical reflection on a cosine to start us at the minimum, we have avoided having to use a C value as well. So let's just throw this all in. Y equals A is 7, cosine, oh, I just forgot vertical reflection. It needs to be -7, my mistake. Square bracket, B value is 2 pi over 5, bracket X, I guess. There's no C value, so I'll end the bracket there, square bracket, and then plus D, so plus 15. And that right there should model the situation we've just created just now. All right, a couple more parts to this. What is the height of the blade after 4 seconds? Well, here's what's nice. Remember, X was your time, and height was your Y. So in other words, you can just throw X is 4 into that old equation back there. So again, the old equation we had was Y equals -7 cosine, it was 2 pi over 5, 1 second. There we go, 2 pi over 5, X plus 15, got it. So 2 pi over 5, X plus 15. Literally just take X is 4 and throw it into here. Now remember, you need to be in radian mode in order to get this to work. So I will do that. If I switch to radian mode first, because my calculator was in degree mode there, -7 cosine 2 pi over 5, I put that in its own set of brackets, times by 4, and then plus 15. Then we can say y equals, I guess we'll just round to the nearest tenth, 12.8, and we must assume that's meters. So the height of the blade after 4 seconds would be 12.8 meters. If I look back at the really rough sketch I did, 4 seconds would be about right here. And yeah, that does look like it'd be about 12 something meters right there. So that does make sense. Question D, for how long is the blade more than 17 meters above ground during one cycle? Well, let's look back at the drawing we did here. 17 meters would be about right up here. So we're going to look at how long it was above that 17-meter point, so between this time and this time. Now, there's not really going to be an easy way of solving this without using a graphing calculator. Like, I mean, you could say that y is 17 and you could solve for x a couple times, but you have to be mindful where cosine is going to be positive or negative. Long story short, that would be a really bad idea. What I would do personally is I would graph this equation in your calculator. Don't mind me as I throw this in right now. You could do that as well. Throw this in your graphing calculator, so -7 cosine, and then I really be careful with that 2 pi over 5. I put it in its own set of brackets, times by x, plus 15. And then you'll also want to make sure you change your viewing window. So I'm going to set my x min. My x min right here, of course, would be, I'd say, about 0. So x min is 0. My x max I can set to 5. The scale you can set to whatever you want. I'll just leave it as 1. My y min I'll change to 0. My y max I'll want it about 20. You know what? Usually you'd set it at 22. I'll give myself a little wiggle room. I'll say it's 24. And then my y scale I'll just set at 5, just so it's not so cramped. And when I graph this in my calculator, ooh, I must have, oh, I cleared it somehow. That's weird. My mistake. Sorry about that. I'll replug that in. Something cleared it on my calculator. It was like, when I graph this in my calculator, nothing shows up. That was weird. Divide by 5, x plus 15. There we go. Now when I plug this in my calculator, it actually graphs pretty much exactly what I drew here. And again, we want to find where it's going to be above a height of 17. So it's nice and all well and good to have this graph here, but the one other thing that we should graph on there is y equals 17. So that'll actually draw a horizontal line directly across the 17, only showing the top parts of this function. If I go second trace, maybe I should write that down, write it right up here. If I press second and then trace, and then trace, there you go, and then find the intersect, I want to find these intersection points and then subtract the times, because this is going to be at, like, let's say 2 seconds, and this will be at, like, I don't know, 4 seconds or something like that. I want to subtract the 2 times. That's basically what I'm getting at here. So anyway, find those intersection points. I'll do the one on the left first. Excuse me. Finding the one on the left, I got a time. You know, I will jump to the other thing. So the one on the left, I got a time of 1.48 seconds. And then the one on the right, I will do as well. Second trace down to intersect. Find the one on the right. My calculator is taking a very long time to move my cursor over. You can thank a TI-83 here, not a TI-84. Sorry about this. I know this is super exciting. Anyway, what I find for my right is I'll round to the nearest 100, 3.52 seconds. So for how long is it above that? Well, it first went above 17 meters after this many seconds, and it went under 17 meters after this many seconds. So just find the difference between these two. So in other words, we'll go 3.52 minus 1.48, and that actually is going to give us 2.04 seconds. That's how long it's above that 17 meters above ground. So 2.04 seconds during that first cycle. Last question here, at least I think it is. Yeah, totally is. Last question here, we'll get through this quick. It's about a tide in the harbor going in and out. So what are the maximum and minimum depths of the harbor? This one we can do without even graphing anything right off the bat here. Notice the maximum and minimum depths are going to be based around your midline and your amplitude. Your maximum is going to be where you take your midline and add your amplitude to it. So it'll be 17. And our minimum is going to be where we take our midline and we subtract our amplitude from it. So it would be 7. So that is our maximum and minimum depths, and I guess we better put that in meters because that's what the question is asking for. Part B, graph the function for 2 cycles. Ooh, 2 cycles. Well, it doesn't tell us where we start, but if we look at our formula itself, it's a cosine function with no phase shift. So cosine functions without a phase shift are going to start at their maximum point. So we got to be pretty careful with how we set this up. Personally, what I'm going to do is I'll say, all right, we want our maximum at 17 and our minimum at 7. I bet we'd even be able to do it one block at a time here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, what am I doing? Why am I counting from there? We want 10 above this to get to 17. What am I doing, guys? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That should be 17. That totally is. So there's our 7. There's our 17. The midline, of course, we know is right in between those two. 1, 2, 3, 4, 5. That's at 12 right there. We're going to start at our maximum because it's a cosine function. We want 2 cycles. Well, a cycle, we should find the period before we do that. The period, remember, is equal to 2 pi divided by b, and b in this case is 1/2. So 2 pi divided by 1/2 is actually going to be 4 pi. That's a really bizarre cycle to have, especially where t is time, but you can have 4 pi seconds. That's like, 4 pi is like 4 times 3.14. It's like 12 something, right? So 12 something seconds is how long it takes for, or not seconds, hours. 12 something hours is how long it takes for this to go through a whole cycle. Anyway, what we should get at here is I will actually label my x-axis using pi instead, as weird as that is. And again, that is your time, and this is your depth. So if we want 2 cycles, 1 cycle is 4 pi. How about we estimate that every pi will be about 4 blocks? So we'll say that's pi, 2 pi, 3 pi, 4 pi. 1, 2, 3, 4 pi. So in other words, that's, we'll just label every second one. 2 pi, 4 pi, 6 pi, 8 pi. There you go. 1 full cycle is 4 pi. We found that from finding our period here. So we're going to be at the maximum point again at 4 pi. So I'll follow that up right to my maximum again. And then it'll be at the maximum once again after another 4 pi. So at 8 pi, we're at our maximum here. In between 2 maximums, so at 2 pi, you're going to be at your minimum. So there'll be that point right there. Same with between these 2 maximums at 6 pi, we're going to be at our minimum right there. If you want, you can draw a midline from y is 12 or d is 12, I guess I could say, to help guide your graph as well. And then, of course, right in between your maximum and your minimum, you're going to be on your midline. So right here, right here, right here, and right here. Now that should be more than enough to draw a real good sketch of our graph here. So down, and then a trough, and then a peak, and then a trough, and then a peak, and I'll just stop right there because that is 2 cycles going from a max to a max, and then another max to another max. What's the period of the tide? Hey, we already solved that. Whew, feels good to be done a question like that. So awesome. Just a matter of breaking down all the little components. We used every single piece of that, including the fact that we were using cosine to help us draw this graph here. So we're done. So for today, I want you to work on these questions right here, page 276, questions 6, 9 to 13, 18, and 19. These are super important to get these done. This will really help get you some practice on this one. And again, as always, if you have any questions, please let me know. Talk to you soon.